A planet may begin as a dust grain smaller than the width of a human hair. It drifts inside a vast disk of gas and dust, orbiting a young star with the entire disk. Gentle collisions make grains stick, and the clumps grow into millimeter and centimeter-sized pebbles. Then growth becomes difficult. Faster impacts can bounce or smash the fragile clumps apart. The crucial leap comes when gas structures and the dust's feedback on the gas crowd many pebbles into the same dense band. Once that patch becomes dense enough, collective gravity takes over and collapses the swarm into kilometer-scale planetesimals. From here, bigger bodies have stronger gravity. They bend nearby paths and sweep more material into themselves. Repeated collisions and mergers build planetesimals into planetary embryos, ranging from moon-sized to Mars-sized. But the disk is not uniform. Close to the star, heat keeps water ice from surviving, leaving mostly rock and metal. Beyond the snow line, stable ice adds much more solid material, so planetary cores can grow faster. If a core becomes massive before the gas disk disappears, it can capture hydrogen and helium and become a gas giant. Worlds that miss that window keep growing more slowly through rock, ice, and later giant impacts. Young planets also exchange angular momentum with gas, dust, and one another, causing migration, resonances, and even ejections. So a planetary system is not a fixed assembly line. It is a long evolution rewritten by collisions, gas, and gravity. From one grain to one world, the key is not a single miracle, but a chain in which each mechanism hands scale to the next. Next, what is gravity, and can space-time really bend?